say the question. A piston cylinder device initially contains air at 150 kPa pressure and 27 degrees centigrade temperature. So at this state, the piston is resting on a pair of stops, as you can see in this figure, and it is the volume is given 400 liter here. You can see. So the volume V on 400, pressure P on 150, T on is 27 degrees centigrade. So the mass of the piston is such that 350 kPa pressure is required to move it. Okay, so the piston, what it says, if you actually want to move this piston, we need pressure 350 kPa. So we have 150 kPa right now. So that means we actually need more pressure. So that means actually we need to heat the air. So the air is now heated until the volume has doubled. So the volume is given 400 liter. That means it will be 800 liter. Okay, so the air is now heated until the volume is doubled. So we'll put the the heat, and you can see the heat is supplied from the surroundings to this system. You can see this arrow here. So we need to calculate the final temperature. So we know the initially, like this stage 1, the pressure was 27, and we don't know actually what is the final temperature, so we need to calculate that. Work done, we calculated work for a couple of problems, so we'll calculate that, and the total heat transferred to the air. So the three questions. So at first, from this drawing, actually we need to write down some assumptions. So if we say, so the first assumptions, let's say, we'll have a couple of assumptions here. We'll air, in this case, we will consider air is an ideal gas, and because it is in high temperature and the low pressure relative to the critical point value, so we'll consider this is an ideal gas. Okay, this system it is a stationary system. So the system, our assumption is the kinetic energy and the potential energy here, it will be 0. So what you can say, it is a stationary system. So the kinetic energy, that means the change of kinetic energy delta K E, or the change of potential energy delta P, it will be equal to 0. We'll make another assumption that there is no electrical shaft or other forms of work involved. Okay, only the moving boundary work. So no electrical work, no shaft work, and no other forms of work. I'm not writing that on. And the volume, initially the volume was 400, and we need to make it double. So the volume remain constant until the piston is moving. This is actually true. So if the piston is not moving, that means the volume will not change. So the other assumption is the volume remain constant until the piston starts moving, and the pressure remains constant afterward. So we need, actually we need more pressure if we want to move this piston. So once it starts moving, you look here at this figure, this is the PV diagram, guys. So in this PV diagram, this is the state 1, the pressure is 150. So if we want to move this piston, we need more pressure. So temperature, so applied temperature, then pressure increased, and at this point pressure becomes 350. That means that piston start moving. So at this point, pressure will remain constant after that, but volume increased. You see, initially the pressure was the volume was 400 liter. So and then you see it becomes double. That means the 800. That means if we consider it in meter cube, then it is 0.8. It was given in liter, and we said it is in meter cube. So you know how to convert liter to meter cube. So I think that's all the assumptions. And another thing is, when you start analysis, when you start solving this problem, you see this is a closed system problem. So no mass cross the system boundary. So that's the thing, and we will now calculate the boundary work. So keep in mind, the first thing is the final temperature, then work done, then the total heat transfer. So if we start with the first part, that means the final temperature. Okay, the final temperature. So as we said, air is ideal gas here. So final temperature means we will calculate. So this is the initial state, this is the final state. We know temperature here, T1 equal 27. So we need the temperature for T3, right? We need this. So we will actually calculate the temperature, and we will apply the the ideal gas relations for this state 1 and state 3. So from the ideal gas relation, from ideal gas relation, P1, V1, T1, it is equal P2, V2, T2. But here we are applying this ideal gas equation for state 1 and 3. So it will be P3, V3 and T3, right? So here we know everything, but we don't know T3. So let's substitute all the values. So P1, it is actually 150 kPa, and V1, we know if we say okay, V1 is just V1, this way it's 0.4, but put this way and see how it goes, and it is 27. So if we convert it into Kelvin, plus 273. V3 actually 350 kPa, and V3, so it will be double, so 2V2, okay, and then T3. Then what you can do, guys, you can simply just eliminate this term, so it should be 2V1, not 2V2. So you can eliminate this V1 and V1, so it should be 2. And if we do some simple calculation, so this T3, it will be 1400 Kelvin. So this is actually the final temperature, T3. So now if we want to calculate the work done, you can remember the second part was the work done by the air. So the work done by the air, you all know, guys, if we actually want to calculate the work, then we can easily calculate the area underneath the process curve. So here the process curve starts from here, and this is the final state. So if we calculate the area underneath this process curve, so see, it will be a rectangle. It will be kind of rectangle. If you look here, this is actually a rectangle. So if we calculate the area of this, we can do it from the PV diagram, but let's calculate the area. So the work done from this final state, initial state 1 to the final state 3, we can write this way. The work done, it is, we can say W, or we can say 1 to 3. That means the state 1 to state 3. We can write it is equal to the area under the process curve. Area under the process curve. Okay, process curve. So what will be the area, guys? So this is, I said it is kind of a rectangle. If you can remember, for rectangle the formula is the height into the width. I showed you for other problem. So here we will say the height, this is pi, and the width is delta v. So pi, it is actually the pressure of the rectangle, okay, and this delta v, this is actually the change of the volume. So here we know the pressure, it is pressure for rectangle, it is actually the pressure for this high state here, the maximum pressure. This is the pressure is 350. So we can say it is 350 kPa, and delta v, that means the change of volume. So change of volume is 0.8 minus 0.4 meter cube. So it will be 140 meter cube and kPa. or if you want to convert it into kilojoule, guys. So this is the kilojoule means you need to just write this way: 140 meter cube kPa, and 1 kilojoule, it is actually it is equal meter cube by kPa. You will eliminate this term, so it will be 140 kilojoule. You know how to convert meter cube kPa to kilojoule, so I believe I do not need to explain this on to you. I believe all of you know this. So this is actually the second part, how to calculate the work done by the air. And now the total work transferred to the heat, total heat transferred to the air. So actually now we will use the energy assumptions. If you can remember, I showed you earlier when I explained the theories. So this question is total heat transferred to the air. So total heat transferred to the air, we can actually calculate this way, guys. Let's say this is question C. So the heat transfer, we will calculate the heat transfer. So if we use the energy assumptions, so the energy assumption is the energy in, the energy out, it will be equal to the delta E of the system, right? So the energy entering and energy converting into work, it will be equal to the change of the energy in the system. It could be internal, it could be kinetic or potential, or any form of energies. So, and this is actually we can say the net energy transfer. So in other words, I explained earlier, this energy in, it means the heat, right? That means we are providing heat. This energy out means we are getting the work, okay, the work as the output. I explained, if you see the first video, the work and heat transfer that I uploaded in UTS Online, then you will see this energy, it means actually the heat. This energy out means it is the work. And the other thing, this, if you see delta E, that means I told you this is the internal energy. U is the internal energy. And we know, from the formula U, the internal energy, you can say mass into the specific internal energy. Here U is capital U, this is a small u. So it is mass, it is a specific internal energy. So actually in our problem, the heat, we have three states. So the one is the initial state, 3 is the final state. So what we will do, we will consider the internal energy for state 1 to 3, because our the heat transfer is happening this way. It was our process, it is 1, it is 2, it is 3, right? So it was happening this way. So now what we will do, we can write down this equation, guys. Let's say this is equation 1, so we can write it like this. And if we substitute this delta U equal mp, delta U, it is actually change of the the internal energy. So we can write it like this: Q in minus the work output, it is equal m v3 u3 into m u1, because this is the change of the energy. Our system is changing from 1 to system 3, so we can say this, it is actually m3 mu3 minus mu1. So from here, this is the relation that we need to use, and we need to calculate the heat transfer. That means we need, guys, we need this Q in. Okay, we need this. We already calculated the work in our second part of this problem. We already calculated the work done is 140 kilojoule. So two other thing here, this U3 and U1, we can get it from the table, but we don't know the mass. So how we can calculate the mass? Look what I said, we need to calculate the heat transfer, right? The total heat transfer to the air. So this is the input, we need to calculate that. The work, we already got the work from the second part of this problem. U3 specific volume, U1 and U3 we can get from table, but M is unknown. So from the ideal gas problem, what we can do, we know from ideal gas relation PV equal mRT. So what we can do, we can write like this way: P1 V1 equal mRT1, or M equal P1 V1 and RT1. P1 is 150, V1 is 0.4, R gas constant 0.287. It is kilopascal per meter cube, per kg Kelvin, and the temperature T1 is 300 Kelvin. So this is meter cube, the V1, and the pressure, it is kPa. So it will be 0.697 kg. We got the M, and now the internal energy we need to calculate. The material in this problem, it is air. We are solving this problem and the material is air. So for air, U1 temperature is 27 plus 273, that means it is 300 Kelvin. Final temperature, you can remember, we got it is 1400 Kelvin when we solved the first part. If you remember, we calculated the final temperature at 1400. So now if we want to solve this, we know the work output, we know the mass, we need U3 and U1. So U3 means the internal energy at 1400 Kelvin temperature. U1 means the internal energy at 300 Kelvin temperature. So it is actually table 17, the appendix 17, A17. Okay, so from your textbook that I told you. So from table A17, it is for the air properties, internal energy for air. So U1 at 300 Kelvin temperature. So it is actually 214.07 kilojoule per kg. And U3 at 1400 Kelvin temperature, it will be 1113.52 kilojoule per kg. Okay guys, so we have U1, we have U3. See, we got U1, U3, we got the mass is this. Okay, so M equal, we got this, and we got the work. So now we need to substitute all of these values, and then we will get the total heat transfer. So what we can write here is the Q in minus work out, it is equal M U3 minus U1. So this is our ultimate target. The heat transfer, will calculate that. Work output is 140 kilojoule, mass 0.697 kg, and the U3 is 1113.52 minus, it is 214.07, it is kilojoule per kg. So if we simplify this, the Q in, it will be 767 kilojoule. So this is actually the the Q in we got. So, and it is also positive, isn't it? That means if we had the system like that, you can remember we had the system like a cylinder, a piston here, okay, and we had the air here. This is surroundings, right? Surroundings. Okay, so the heat, that means it's transferred to the system, and then it is positive. So I explained earlier. So here we got the heat transfer is 767 kilojoule. As it is positive, that means yes, heat is transferred to the system. So that actually what we did. If I do a quick review, guys, um, we used some assumptions here, and we just draw the PV diagram here. So when we calculated the work done, so finally the final temperature, initially we calculated the final temperature. We used the ideal gas relation P1 V1 T1 P3 V3 T3. Everything was known, so we got T3. So work done, I told you, when we calculated the work done, it is the process curve, it was like this. Process curve was, it is 1 2 3. So underneath this process curve, it is a rectangle. We had a rectangle like shape, so we used a height and width. So pi and delta v, we used the same relations previously. So pi is the pressure and the delta v is the volume change. And when we calculated the heat transfer, we used the energy assumptions and energy balance relation. We used the definition of the internal energy, and we calculated the mass from the ideal gas relation here, and we calculated the air properties from table A7. This is the appendix table from the appendix, you will get it from there. So U1 U3, U1 means the initial temperature 300, U3 means 1400 Kelvin. So and then we substitute all these values and we got this rate of heat transfer. I think that's it.